Welcome back. In this video lecture, we're going to discuss section 2.3 from the textbook, one quantitative variable, measures of spread. You can see from our outline here that we have four subsections that we'll want to cover. First, the standard deviation, then the 95% rule, the standard score, and the 5-number summary. Let's begin with the standard deviation. A good way to get started thinking about the standard deviation is to consider the following problem. So here are the dot plots for the temperatures on April 14th for San Francisco and Des Moines for the past 21 years. The first question is, approximately what is the mean of the temperature data for Des Moines? So down here we can see the dot plot for the Des Moines temperatures for April 14th, and if we're looking for the center of this dot plot, the mean of this dot plot, we're going to put it somewhere in this area. Let's just call it 54 degrees. It looks like the data will be balanced fairly nicely at around 54 degrees. If we ask the same question of San Francisco, right, approximately what is the mean of the temperature data for San Francisco, we're going to look at the San Francisco dot plot, temperature data dot plot, and we're going to see that it too seems to be balanced pretty nicely around 54 degrees. So for both cities on April 14th, for the past 21 years, we're going to see an average temperature at around 54 degrees Fahrenheit. Now, question 3 gets to the heart of the matter. You have to predict next year's temperature on April 14th for each city. In which prediction will you have more confidence and why? Now, I think in both cases it makes sense to guess the mean temperature for next April 14th. It makes sense for both cities to say, I think it will be 54 degrees in Des Moines, Iowa, and I think it will be 54 degrees in San Francisco on April 14th of next year. Now, in which prediction do I have more confidence? Well, I feel a lot better about my guess for San Francisco because although I may be wrong, at least based on the historical trend, I won't be wrong by too much. The data is much more closely packed around the mean than it is in Des Moines, Iowa. In Des Moines, even though I'll guess the same 54 degrees Fahrenheit for the next year's temperature on April 14th, I also have from the historical record the sense that the temperatures vary widely around that mean of 54 degrees. So I'll have a lot more confidence in my guess for the temperature in San Francisco than I will in Des Moines, Iowa. Now, we can capture this idea very nicely by examining the concept of a residual. So let's take a look at that next. To get started thinking about residuals, let's consider this small data set S. You can see the range of values that S contains here, and you can see the dot plot of those values below here. Now, the mean, which I calculated, is 16, and I can impose that on the dot plot here with that vertical red bar that you see. You can see that the data is nicely centered, nicely balanced around that mean. Now, what is a residual? Every value in the data set has a corresponding residual, and a residual is just the value of the data point, minus the mean. So for example, if I look at the data point 13, its residual is 13 minus 16, or negative 3, which I've pictured here. If I look at the data point 20, its residual is 20 minus 16, and I've drawn that residual here. So one way to think about a residual is it's the directed distance from the mean to the data point. So I start at 16. If I move 4 units in the positive direction, I get to the data point 20. If I move 3 units in the negative direction, I get to the data point 13. So each and every number in this data set has a corresponding residual that I can calculate very simply using this formula. Now, to begin the calculation of a standard deviation, we have to imagine taking all of the values of the data set S, and below each value in the data set, let's write its corresponding residual. So each of these residual values was computed simply by taking the value at the data point and subtracting the mean of 16. So you can see each residual has been calculated. Now, in order to do the standard deviation calculation, we need to take this one step further. We need to form another row where each residual has its corresponding square beneath it, right? So 1 squared is 1, negative 4 squared is 16, and we continue that process of forming the row of the squares of the residuals. So just to recap, we have the first row that contains the data points, the second row contains the residuals of the data points, and the third row contains the squares of the residuals of the data points. The next step in the calculation is to sum all of the squares of the residuals, and this is sometimes called the SSR, the sum of squared residuals. And this really just entails adding up all the numbers in this row, and when we do that, when we find the sum of all the numbers in that row, we get the value of 80. And we are now past all of the hard calculations in computing the standard deviation. The last step is to find the standard deviation by taking the square root of the SSR and dividing it by n minus 1, or 1 less than the number of data points in the sample. Now, our sample contained 9 data points, and so we're going to take our sum of squares residuals, the 80, and divide it by 9 minus 1, or 8, and then take the square root of that. Now, 80 divided by 8 is simply 10, and so we're computing the square root of 10, or we're getting the number 3.16. So that is the calculation of the standard deviation. The standard deviation for the set S is 3.16. Now, for the most part, we'll be working with very large data sets, and this would be a very laborious calculation to do on a very large data set. So what I'll show you to do how to do next is to take the same set S and throw it into StatKey and have it compute the standard deviation for us. Now, what's lost in having StatKey do the calculation for us is you lose some sense of where the standard deviation comes from. So it's very important for you to remember that the standard deviation is intimately connected to this sum of the squares of the residuals. And so you always want to retain that sense of what the standard deviation is, even if the computer is calculating it for you. So let's go on, and I'll show you how to take exactly the same data set and compute it using StatKey. If we're going to use StatKey to find the mean and standard deviation of a data set, for example, this data set S, I have to find a way to get that data into StatKey. And as I showed you in a previous video lecture, I can simply write all of the elements in my data set in a single vertical column. In this case, I've given my column the name My Data. You don't have to do that. I'm going to copy that out of my text editor. I'm going to move over to StatKey. I'm going to select one quantitative variable. By default, it loads the file called mammal longevity. I'm going to edit that data set. I'm going to wipe out all of the existing data and simply replace it by My Data. I'm going to uncheck this box because I don't have a column that identifies the rows. And I'm going to leave Data has a header row checked because I have a name at the top of my column. I'm going to select OK. And I can see that all 9 of my points are appearing in my data set. The mean is 16, as we calculated before. And the standard deviation is, as calculated before, 3.162. So this agrees with exactly what we got when we did the calculation using the method of residuals. Okay, so for the most part, we are going to let StatKey compute standard deviations for us. Nonetheless, I do want you to remember that the standard deviation is connected to the residuals through the sum of the squares of the residuals. So I do want you to remember that because that's going to be a helpful way for you to think about what the standard deviation is doing and how it is being calculated, even if you've turned the calculation over to a machine. Okay, I want to look at one last thing in this subsection before we move on to the next subsection. And I've labeled this slide Fun Facts about the Standard Deviation. So some things to remember about the standard deviation. So remember, even if we're having a machine calculate it for us, the standard deviation is the square root of the sum of the squares of the residuals divided by n minus 1, where n is the number of points in our data set. The standard deviation, therefore, is an average of the distances of the data points to the mean. The standard deviation is always going to be positive. And finally, the standard deviation will always retain the same units as the data set itself. So if your data is being measured in feet, the standard deviation will also have units of feet. Now I have a little asterisks here on claim 2 that the standard deviation is always positive. This is technically not true, and I'm sorry about that. It turns out if all of the data points are the same, then in fact the standard deviation is 0. There is no variation in the data if all the data is the same. But if your data has any variety in it at all, the standard deviation will reflect that as a positive number. Okay, so that draws a conclusion to this part of the notes. We've concluded our work on the standard deviation. We are now going to move on and talk about the 95% rule. The 95% rule is a rather remarkable law of nature, and it says something like this. Imagine that your distribution has a bell shape, so we're thinking that the dot plot or the histogram of your data has this nice bell shape. What the 95% rule says is that 95% of your data, 95% of the points in your dot plot, for example, are going to land between x bar minus 2s and x bar plus 2s. So once we know the sample mean and once we know the standard deviation s, we can find the interval from x bar minus 2s to x bar plus 2s, and we can know that 95% of our data is going to land inside that interval. Now that means also, because of symmetry, that 2.5% of our data will land here in this left tail, and 2.5% of the data will land in that right tail. All right, let's look at the claim of the 95% rule. It says, if a distribution of data is approximately bell-shaped, about 95% of the data should fall within 2 standard deviations of the mean. Put another way, the middle 95% of the data in a sample from a bell-shaped distribution should fall in the interval from x bar minus 2s to x bar plus 2s. Now, to get really comfortable with this concept, I want us to work a number of problems that deal with this 95% rule. In the 2019 Spinks Run Fest, 943 participants ran either the marathon or the half marathon. Here's the dot plot and a summary of the variable called pace. This is the pace with which the runners ran their various races. Here's the dot plot. We can see that it's approximately bell-shaped. Now we want to find the interval that contains the middle 95% of the pace values. Now I'll show you how to work this out using the overhead camera, but 2 pieces of information that we want to bring with us is that the mean of this pace variable is 10.189, and the standard deviation of the pace variable is 1.931. So let's go to the overhead camera and work out find the interval that contains the middle 95% of the pace values. So our goal in this problem is to find the interval that carries the middle 95% of the data for this pace variable from the Spinks Run Fest. From the summary statistics, we pulled out the sample mean, which is 10.189, and the sample standard deviation, which is 1.931. So to find the cutoffs for the middle 95% is actually pretty easy. We just have to do a little bit of arithmetic. Our first calculation is going to be x bar plus 2 times s. And that's simply going to be 10.189 plus 2 times 1.931. And that gives us our upper cutoff at 14.051. Likewise, x bar minus 2 times s, which will be 10.189 minus 2 times 1.931. Gives us a lower cutoff of 6.327. So we know that 95% of the participants in this race will have a mile pace between 6.327 and 14.051. There will be some people that run at a slower pace. There will be some people that run at a faster pace, but this captures 95% of all the participants. So the image that you should have in mind is something like this. Here's the dot plot for the race. We know that that central axis is centered on the x bar, which is 10.189. But we've now found these 2 cutoffs. And we know that 95% of all the participants are going to be in this range between 6.327 and 14.051. So that's our application of the 95% rule. Let's go back to the course slides. In this problem, I'll show you how we can take a dot plot, which is bell-shaped, and from that dot plot, we can infer the standard deviation. So in other words, we can use the plot itself to help us understand what the underlying standard deviation is. And this is, again, using the 95% rule. So here's the dot plot for the variable pace in the 2019 Spinks Run Fest. We know that there were 943 participants. Now we want to use the 95% rule to estimate the standard deviation S of the pace variable. So we're kind of playing the game in the opposite direction here now. We're going to use the 95% rule to estimate the standard deviation of the pace variable. So let's go to the overhead camera and I'll show you how we can use the dot plot to estimate the standard deviation. Welcome to the overhead camera. We're going to now use the 95% rule to try to estimate the standard deviation of this data set. Now, how's this going to work? What we're going to do is we're going to take these 943 data points and we're going to try to carve out the upper 2.5% and the lower 2.5% so that we can identify the middle 95%. We're going to find the two boundaries for that middle 95%. We know that they're spanned by 4 times the standard deviation. So knowing the size of this gap should give us a good measure of the standard deviation. So our first job is to figure out how many points would be in the upper 2.5% and how many points would be in the lower 2.5%. I'm just going to do this kind of back of the envelopes kind of calculation here. I'm just going to kind of do a rough and ready calculation. You don't have to be super exact on this, so you just kind of get a rough idea of how big the upper 2.5 and lower 2.5% are. So what I'm going to do is I'm going to take the 943. I'm just going to move the decimal place, 94.3, or let's just call it 94. That represents 10% of the data. Half of that, which would be 47, will represent 5% of the data. And half of that will represent 2.5% of the data. Well, now, it's easier to work with an even number, so let's just call it 48. And so we'll think of 24 gives me 2.5% of the data. Now, all I have to do is start from the top and count down to 24, and then start from the bottom and count up to 24, and see where the 24th point from the top and the 24th point from the bottom are. So now, all we have to do is just count. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4. So there's the 24th point from the top. And really what I want to do is mark the column that that's in. I want to have that point marked. From the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4. There's the 24th point from the bottom. I'm going to mark that location. So there's my gap. This gap is spanned. This is the middle 95% here. And this gap must be spanned by 4 times the standard deviation. Now all I have to do is estimate these positions on the x-axis, and you don't have to be too exact here. I'm just going to do a kind of a rough approximation. I'm going to call that 7. And I'm going to call this 15. All right? The gap from 7 to 15, that's 8. And we know that that 8 has to be spanned by 4 times the standard deviation. And that's going to give me an estimated standard deviation of 2. Now, if you remember from our data, we know that the standard deviation is on the order of 1.93. So you can see, using our kind of simple counting method here, we can get a very good approximation for the standard deviation using this 95% rule. So let's head back to the notes, and I'll show you one more application of this 95% rule. Let's work one last problem using the 95% rule. And this is essentially reworking the exact same problem we just finished working, but now with actual data points instead of the dot plot. So we'll see that it's very similar to the work we've done already. So here are the left and right tails for the pace variable for the 2019 Spinks Run Fest. There were 943 participants. We're going to use this information to estimate the standard deviation of the pace variable. So here we've got our data arranged from the smallest to the largest number. And as before, we have to carve out the lowest 2.5% and the highest 2.5%. So we need to take 2.5% out of the left tail and 2.5% out of the right tail. Now, as we saw in the previous problem, that means we have to find the lowest 24 and the highest 24 entries in our data. Now, luckily, these are arranged in columns of 8, so that's going to be the 8th, the 16th. There's the 24th lowest value. That's at 7.03. That's going to form our left endpoint. We need to do the same thing from the other end, and so there's 8, 16. There's our 24th number counting down from the right tail, the top of the right tail, so that's 14.76. So what I need to do is take 14.76 minus 7.03 and divide that by 4, because that gap has to be spanned by 4 standard deviations. So we can easily do this calculation. We need to take 14.76, take away 7.03, and we need to divide that by 4 because that gap has to cover 4 standard deviations. And we find by doing it by this method, we've got an estimated standard deviation of 1.9325. And that agrees very nicely with the standard deviation that is calculated using StatKey. And it's also very close to the standard deviation that we estimated using just the dot plot. Okay, so that brings an end to this subsection on the 95% rule. And now we're going to go off and work on this subsection called standard score. So suppose a data set has a sample mean x bar and a sample standard deviation s. The standard score, or z-score, for the data value x is computed by taking x, subtracting the mean x bar, and dividing that by s. Another way of thinking about it is I'm dividing the residual by the standard deviation. So the important thing to take away here is that each and every element in the data set is going to have a corresponding z-score that I calculate using this formula. Now we're going to do some calculations involving z-scores in just a bit. But before we do that, I want to look at some fun facts about standard scores so that you'll have some familiarity with how the standard score works and how it gets used. So fact number 1, z is a dimensionless quantity. It has no units. A z-score is a pure measure of deviation from the center. If z is positive, then the corresponding value x must be bigger than the mean. And if z is negative, then the corresponding data value x must be less than the mean. In other words, the sign of z, whether it's positive or negative, tells us whether the data value is above or below the mean. And finally, if the data set is bell-shaped, then 95% of the values will have a z-score between -2 and 2. And so we have a quick way of assessing how extreme something is in the context of some bell-shaped data. If you have a z-score that's bigger than 2 or less than -2, then you know you are in an extreme situation. You're either in the upper 2.5% of the data or you are in the lower 2.5% of the data. But in either case, you're in some extreme situation. So to get a feel for this, imagine the following scenario. So recall the temperature data that we looked at earlier comparing Des Moines and San Francisco on April 14th. Suppose on a particular April 14th, both cities were experiencing temperatures that would have a corresponding z-score of 2.3. Now we know in both cases, those z-scores being positive puts them above the mean. Those are warm days. And since they're both bigger than 2, we know that they're very, very extreme. Those are in the upper 2.5% of temperatures that will be registered in either San Francisco or Des Moines. So we know that both cities are experiencing the same level of extremity. Now, we do know, though, that Des Moines has a higher standard deviation. The temperatures have a larger standard deviation. So we know that Des Moines is absolutely warmer, absolutely hotter that day than San Francisco. But relatively speaking, we can say that both cities are experiencing the same level of extremity in the temperature. Okay, so both cities would have a reason to lodge a complaint with Zeus, the god of weather, right? They both are experiencing temperatures that have z-scores of 2.3. Now, what I want us to do next is to compute some z-scores and see how z-scores can be used to help us form comparisons. Let's consider the following problem. The SAT and the ACT are two popular tests of preparation for college. The distribution of test scores is bell-shaped in each case. Here's some information about these test scores. So we know that by considering historical data that the SAT has a mean of 1,059 and a standard deviation of 210, while the ACT has a mean of 21 and a standard deviation of 5.4. Al's score on the SAT was 1,332. Bob's score on the ACT was 29.1. Which had the better performance? Explain. Now what we're going to do is we're going to compute the z-score for Al and we're going to compute the z-score for Bob, and having standardized their scores, now we can compare their performance. So this is one of the nice uses of z-score. So let's go off to the document camera and we'll work out the details in this problem and see who had the better day. Welcome to the overhead camera. So we're now going to see if we can compare Al's score on the SAT with Bob's score on the ACT. We want to know who had the better day. Now remember, we can't just compare these numbers as such. We can't compare the 1332 and assume it's better than the 29.1 just because it's the bigger number. We have to compare them relative to the field, relative to the people that took the same test. Al took the SAT and Bob took the ACT. So what we're going to do is compute the standard score for each of these and compare their standard scores. That puts them on the same scale. All right, so for Al, his standard score for his 1332 is going to be 1332 minus the mean for the SAT, which was 1,059, divided by the standard deviation for that SAT, which was 210. And when you do that calculation, you end up with 1.3. So Al has a z-score of 1.3. Now we'll do the same thing with Bob. We're going to compute the z-score for his ACT score. So we take the 29.1, we subtract the mean for the ACT, which is 29, and divide by the standard deviation, which was for the ACT was 5.4. And when we do that calculation, we end up with 1.5. So now comparing these two performances as z-scores, we find that Bob has the higher z-score than Al, and therefore we can say that Bob had the more exceptional day. His score has a higher z-score than Al's, and so we would say that his performance is the more exceptional performance for that day. So this shows you a way that we can use z-scores to compare data across different distributions. So I hope that helps. I want to look at one last problem to close out this section on standard score. And this problem is really getting at the idea of what is exceptional and how will that be reflected in the z-score. So consider this first problem. On July 14th, the 153 employees of Bytegenics have a golf tournament. What can we say about the z-score of the tournament winner? So we're imagining that these golf scores are going to come in. We're going to look at all of the golf scores for the 153 employees. And now we want to know something about the z-score for the tournament winner. Now you have to remember, in the game of golf, the idea is to get a low score. So the tournament winner is going to have the lowest score amongst the 153 employees. In particular, that score is going to be below the mean, and it's likely to be very exceptional. All right, so we would imagine that the z-score for that tournament winner is likely to be, well, it's certainly going to be negative because it's below the mean, and it's likely to be even less than -2. So we're looking for a z-score around -2 or less. That's what we would expect for the winner of the tournament. Now, compare that to this other problem, right? On July 14th, on the very same day, the 503 children at the Rumford Day School have a hot dog eating contest. What can we say about the z-score of the tournament winner in this case? Now, as opposed to the game of golf, the idea of a hot dog eating contest is to eat as many hot dogs as you can. And so we imagine that that exceptional child who ate the most hot dogs is going to have a positive z-score and a z-score that is likely greater than 2. It's going to be exceptional in that direction. It's going to be bigger than the mean and likely to be greater than 2. So what is exceptional? It's all a matter of context. In the case of golf, we would be expecting an exceptional z-score in this case to be a largish negative number, and in the case of the hot dog eating contest, a relatively large positive number. So we have to be careful in how we interpret exceptional in each of these contexts. Okay, that closes off this section on the standard score. And we're going to move on to this next section on the 5-number summary. So before we get working on our 5-number summary in earnest, it's helpful to have the concept of a percentile. And so let's see if we can understand this concept by looking at this figure below. So let's imagine that this blue curve represents a dot plot for some data set. We want to say that 74.2 is the 80th percentile for the data set, because if I were to cut the data set at 74.2, it would leave 80% of the data to the left and 20% of the data to the right. Now, we're already familiar with the concept of a median. A median cuts the data set in half. It leaves 50% of the data to the left and 50% of the data to the right. So another way to talk about a median is it's a 50th percentile. All right, with that in mind, let's take a look at the 5-number summary. So the 5-number summary of a data set S is the list consisting of 5 numbers: the min, Q1, Q2, Q3, and the max. Now, we already know 3 of these. The min and the max are the smallest and largest entries in the data set. Q2 is the median of the data set. So 3 of these numbers are known to us already: min, Q2, and max. Let's talk about Q1. Q1 is the median of the lower half of S. So once you've identified the median, you now have a lower half for your data set, and you now have an upper half for your data set. Q1 is the median of the lower half, and Q3 is the median of the upper half of the data set S. So Q1 is roughly the 25th percentile, and Q3 is roughly the 75th percentile of the data set. So if you think about these, this is the 25th percentile, the 50th percentile, and the 75th percentile of your data set. And that's why these numbers are notated with Q for quartiles. These are splitting the data set into quartiles or quarters, and that's why we use the Q notation in this case. Now, I've got asterisks on lower half and upper half here because we have to come to some kind of agreement about what to do in case the data set is odd. If you remember, anytime you have an odd number of elements in your data set, the median is one of the elements in the data set. And the question is, do we include the median or do we not include the median in the lower halves and the upper halves? And we're going to come to the following agreement. If S has an odd number of elements, then the median should be included in both the upper half and the lower halves of S. Hopefully that's going to make a lot more sense when we come to do some particular calculations. But that's the definition that we're going to go with when we're working on our 5-number summaries. So let's work each of the following problems using the overhead camera. So give the 5-number summary of each of the data sets. We'll work with our first set, a data set called S, and then we'll work with our data set called T. So in each case, we're going to extract the 5-number summary for these data sets. So I will join you at the overhead cam to work out the 5-number summaries for both of these sets, S and T. So our goal here is to find the 5-number summary of this data set S, which I've got written out here. I went ahead and counted the number of points in the data set. There are 14 points in this data set. And I set up my table. These are the 5 values that I'm going to have to fill in. The min, Q1, Q2, Q3, and the max. Now, when I'm doing a problem like this, I usually start with the min and the max because those are easy to find. The min, once the data set is ordered, the minimum is sitting there. In this case, it's 23, and the max is 30. Q2 is going to be the median. I'm going to find that next. The data set contains 14 elements. It's going to have a lower 7 and an upper 7. 1, 2, 3, 4, 5, 6, 7. There's the boundary between my lower 7 and my upper 7. And we can see that we would average 26 and 26. So this is particularly simple in this case. The median, or Q2, is 26. And now I just have to compute the median of the lower half and the upper half separately and report Q1 and Q3. Now I know that I've got 7 elements in my lower half, and 7 is an odd number, so there's a number in the middle that's going to be at position 7 plus 1, or 8, divided by 2. So position 4, 1, 2, 3, 4. There's my value of Q1, and I do the same thing in the upper half, 1, 2, 3, 4. And there's my value for Q3. And so that's an example of how to do a 5-number summary for a small data set. Our goal now is to find the 5-number summary for this data set T. It's already ordered for us. There are n equals 13 data points in here, and we just want to fill out the 5-number summary. Once again, I'm going to start with the easy bits. The 79 is the min. The 119 is the max. So far, so good. Now let's go for the median. We have 13 points in our data set. That means there is going to be a number that sits in the middle at position 13 plus 1, 14, divided by 2, or position 7. 1, 2, 3, 4, 5, 6, 7. So here we go. There's our median, or Q2. And now we have to find Q1 and Q3 by computing a median for the lower half and the upper half. Now, remember in this case, when there is a middle entry in computing the median, we want to include that median in both the lower half and the upper half. So right now, I'm going to be computing the median of this set. And there are 1, 2, 3, 4, 5, 6, 7 elements in that set. And that means that this lower half has a middle element at position 4. So there's our value for Q1. And this upper half, which starts at 103 and ends at 119, also has a middle element at position 4. And that means Q3 will be 108. And so that's how to do a 5-number summary in an example where we have an odd number of elements in our set, and we have to remember to include that median in both the lower half and the upper half. Okay, let's go back to the class notes. I want to work a problem where we're given the 5-number summary and we have to interpret or pull information out of that 5-number summary. So imagine the following scenario. Professor Al teaches organic chemistry. He gives each student in his class a final score from 0 to 100. He assigns letter grades on a 10-point scale. So here's the 5-number summary of his grades for the course. We see that the min is 62, the max is 88, the median is 76, Q1 is 72, and Q3 is 80.5. So, what fraction of his students fail? Well, to fail on a 10-point scale, you have to get a 60 or below, and we can see that none of the students fail his course. What fraction of his students get at least a C? Well, to get at least a C and not a C minus, you have to score at least 72, and we can see that Q1 is equal to 72. That means that 25% of the students are landing below 72 and 75% of the students are landing above 72. So we know that 3/4 of the students, or 75% of the students, are getting at least a C. What fraction of his students get at least a B minus? Well, to get at least a B minus, you have to be scoring 80 or above. Now, we can't be sure about this, but here we are sitting with Q3 at 80.5, and so we know that 25% of the students are scoring above 80.5, so we would conjecture that about 25% of the students, or a quarter of the students, are getting at least a B minus from Professor Al. Finally, if a student were chosen at random from Al's class, what would you predict for his final score? So, knowing nothing about the student, but knowing something about how Al distributes his grades, if we had to guess what a randomly selected student, how a randomly selected student would do in Professor Al's class, we would have to go with the median. We would say, I am going to guess that the student is going to get 76 for the class. Obviously, the student could score below that or above that, but I'm sitting in the center at 76. I feel pretty good about that guess, and that's what I would go with. The last thing I want to look at in this section is the range and the interquartile range. So from the 5-number summary, we can compute the following two statistics. The first is called the range, and that is simply the max minus the min. And the second is called the interquartile range, and that is simply Q3 minus Q1. So IQR here is just short for interquartile range. Now, we're not going to make much use of it in this section. We're simply going to learn how to compute it, or see how to compute it. We're going to make substantial use of that in the next section when we try to identify outlying values in a data set. But for now, let's just get comfortable working with these concepts. So in our final problem here, we're going to work this out using the overhead camera, but we're going to find the 5-number summary, the range, and the IQR of the following data set. So join me at the overhead camera. We'll work out that calculation, and that will draw a close to section 2.3. Our first step is going to be to find the 5-number summary of the data set, and we can quickly fill in some of these elements. The minimum is 19, and the maximum is 33. The set contains 10 elements, and so we can quickly divide it into a lower 5, and an upper 5. The value of Q2 is simply the average of 24 and 27, and so that's going to be 25.5. Q1 is going to be the median of the lower half, and since that's an odd number of elements, we can simply select the middle element. And likewise, the value of Q3 is the median of this upper half, and again, that contains 5 elements, and so we select the third element in the upper half. And so there's our 5-number summary. The range is simply the max minus the min, and so that's going to be 33 minus 19, or 14, and the IQR is the value of Q3 minus the value of Q1, so 33 minus 20, or 13. And that completes our problem.